Have you ever looked up at the night sky and felt an overwhelming sense of wonder, that tingling sensation of being both insignificant and profoundly connected to something far greater than yourself? It's a feeling as old as humanity itself, a moment where the boundaries between science and philosophy blur into something magical. For thousands of years, the stars have been more than just distant points of light. They've been mirrors reflecting our deepest questions about existence, purpose, and the very fabric of reality. Today, we're diving into the mesmerizing intersection of astronomy and philosophy, where the cold equations of the cosmos meet the warmth of human curiosity. Think about the last time you truly stopped to marvel at the universe. Maybe it was a meteor shower streaking across the darkness, or a quiet evening under a sky so clear you could see the Milky Way stretching like a river of stardust. In those moments, it's impossible not to ask the big questions. Where did all of this come from? Are we alone in the universe? What does it mean to be a tiny speck of life in an infinite expanse? These aren't just scientific inquiries, they're philosophical ones too. Astronomy gives us the tools to measure the heavens, but philosophy helps us make sense of what those measurements truly mean. Together, they form a dance of discovery, each step revealing new layers of understanding about our place in the grand scheme of things. This journey isn't just about facts and figures, it's about the stories we tell ourselves to grapple with the unknown. From ancient civilizations who saw gods in the constellations to modern scientists unraveling the mysteries of black holes and dark matter, humanity's quest to understand the cosmos has always been intertwined with our search for meaning. By the time we're done, you'll see the night sky differently, not just as a spectacle of distant suns, but as a canvas for some of the most profound questions we can ask. So let's take that first step together into the vast and beautiful unknown where science and wonder collide. The universe is waiting. Long before telescopes or satellites, our ancestors gazed upward with the same burning curiosity that drives modern astrophysics. The ancient Egyptians aligned their pyramids with celestial precision, turning monuments into stone calendars that tracked the seasons with uncanny accuracy. Meanwhile, halfway across the world, Babylonian priests meticulously recorded planetary movements on clay tablets, not just as data but as messages from the gods. This wasn't mere stargazing, it was humanity's first attempt to bridge the tangible and the transcendent, to find patterns in the chaos of the night sky. Take the Greek philosopher Pythagoras, who heard music in the motion of the planets. To him, the universe wasn't silent, it hummed with a hidden harmony he called the music of the spheres. Centuries later, Galileo's telescope would prove the heavens weren't perfect crystal spheres as Aristotle imagined, yet that poetic vision still resonates. Why? Because it speaks to something deeper than science alone can satisfy our need to feel connected to the cosmos. The Mayans built observatories to predict Venus cycles, the Chinese mapped supernovas as celestial omens, and Polynesian navigators crossed oceans by reading star paths like road maps. Each culture saw different stories in the stars, but all shared one truth: the sky was never just empty space. It was a living storybook, a moral compass, a mirror reflecting humanity's highest aspirations and deepest fears. What's astonishing is how these ancient insights still echo in modern cosmology. When today's physicists describe the universe as a vast quantum web or search for a unifying theory of everything, they're walking the same path as the philosopher-scientists of old, just with better telescopes. The questions haven't changed. How does order emerge from chaos? What invisible laws bind the cosmos? Whether carved on temple walls or written in supercomputer code, our cosmic inquiries remain driven by that same childlike wonder under a starry sky. The tools evolve, but the thirst for understanding, that timeless dance between measurement and meaning, is written in our DNA. Imagine living in a world where everyone believed Earth stood motionless at the center of creation, with the sun, moon, and planets revolving around us in perfect celestial harmony. That's exactly how the universe was understood for centuries until a quiet Polish astronomer named Nicolaus Copernicus turned everything upside down. His revolutionary idea wasn't just about swapping Earth and the sun's positions. It was a seismic shock to humanity's entire sense of importance. For the first time, science suggested we weren't the main characters in the cosmic story, but merely inhabitants of a modest planet orbiting an ordinary star. This was more than a scientific correction, it was an existential earthquake. Think about what that realization must have felt like in the 16th century, when religion, philosophy, and daily life all revolved around Earth's central role in creation. Copernicus didn't just challenge astronomy textbooks, he unwittingly sparked a crisis of meaning. If we weren't at the physical center of the universe, were we still at its moral and spiritual center? Philosophers from Descartes to Kant grappled with this question, realizing that human perception might be fundamentally limited, that what felt true and obvious could be completely divorced from reality. The night sky, once a comforting tapestry of divine order, suddenly became a mirror reflecting our own insignificance. Yet there's a beautiful irony here. While the Copernican Revolution dethroned Earth from the center of the cosmos, it also expanded our intellectual horizons in ways no one could have predicted. By accepting that the universe didn't revolve around us, we gain the humility to study it on its own terms. This shift birthed the scientific method itself, the idea that truth isn't dictated by human intuition, but revealed through observation, evidence, and the courage to question even our deepest assumptions. Modern cosmology, from Galileo's telescopic discoveries to Hubble's glimpse of an expanding universe, all trace back to that pivotal moment when humanity dared to see itself as part of something vast and mysterious. The real lesson of Copernicus isn't just about planetary motion. It's about the courage to confront uncomfortable truths, to let go of comforting illusions in pursuit of a grander, if more humbling, reality. Every time we discover exoplanets orbiting distant stars or detect gravitational waves from colliding black holes, we're standing on the shoulders of that revolutionary idea, that the universe is far stranger and more wondrous than our ancestors ever dreamed. And perhaps that's the most profound philosophical shift of all, realizing that our true significance lies not in being the center of creation, but in our ability to understand it. Johannes Kepler stared at the night sky not just as a scientist, but as a cosmic poet searching for hidden melodies in the dance of planets. Where others saw chaos, he heard whispers of a grand mathematical symphony, an idea so beautiful it bordered on spiritual revelation. This wasn't mere number crunching, it was a passionate conviction that the universe operated by elegant geometric rules, a divine blueprint written in the language of shapes and ratios. His famous 3 laws of planetary motion didn't just describe orbits, they revealed a hidden harmony, as if the cosmos itself were a meticulous composer arranging celestial bodies into perfect polyphonic rhythms. Take his obsession with the perfect solids of ancient geometry, the cube, tetrahedron, and their other symmetrical siblings. Kepler became convinced these shapes secretly nested between planetary orbits like invisible musical intervals. Imagine his exhilaration when Saturn's orbit fit around an octahedron, Jupiter's around a cube, as though the solar system were a colossal wind chime tuned by some cosmic artist. Of course, we now know his exact model was mathematically flawed, but that's almost beside the point. What matters is how his philosophical hunger for harmony propelled him toward genuine discovery. His missteps were as illuminating as his successes, proving that sometimes the wrong question asked with enough wonder can lead to the right answer. This blend of mysticism and mathematics might seem contradictory today, but it's precisely what made Kepler revolutionary. While Galileo dismantled old paradigms with empirical grit, Kepler approached the cosmos with a Renaissance mind equally fluent in equations and aesthetics. His third law, linking orbital periods to distances with poetic precision, wasn't a dry formula but a triumphant shout. "I've heard the music," and in a way he had. Modern astrophysics confirms his intuition. Planetary systems often form with resonant orbital patterns, their gravitational dances echoing the very harmonies he dreamed of centuries ago. There's a profound lesson here about how scientific breakthroughs often begin as philosophical yearnings. Kepler didn't just want to predict where Mars would appear next week. He longed to understand why the universe felt so breathtakingly ordered. That childlike insistence on finding beauty in the machinery of the cosmos still drives researchers today, whether they're hunting for symmetrical equations in quantum physics or listening for gravitational waves rippling through spacetime. The irony, Kepler's harmony of the spheres turned out to be far stranger than he imagined, not crystalline geometries, but the chaotic grace of relativity and dark matter. Yet his legacy endures every time a scientist pauses mid-calculation to marvel at the sublime elegance hiding within the data. Galileo pointed his handmade telescope toward Jupiter one winter night in 1610, expecting to see nothing more than a bright star. Instead, he witnessed 3 small points of light hovering near the planet lights that moved over subsequent nights in ways that defied all existing cosmic rules. Here was the unthinkable: moons orbiting something other than Earth, a direct challenge to the Aristotelian universe where everything revolved around us. His sketches of lunar craters and sunspots shattered another ancient belief that celestial bodies were perfect, unchanging spheres. Suddenly, the heavens weren't a static backdrop for human drama, but a dynamic, messy, and astonishingly alive place. This was more than a scientific breakthrough, it was a philosophical grenade. For centuries, scholars had treated Aristotle's word as gospel, trusting abstract reasoning over direct observation. Galileo's telescope forced a radical question: when tradition and evidence clash, which do we trust? His infamous showdown with the Church wasn't just about astronomy, it was about epistemology, the very nature of knowing. If our eyes, aided by lenses, could reveal truths that contradicted millennia of doctrine, what else might we be wrong about? The answer terrified those in power. Authorities refused to even look through his telescope, proving how deeply fear can cloud curiosity. Yet Galileo's real revolution lay in his method. Unlike Kepler's mystical harmonies or Copernicus' mathematical elegance, Galileo insisted on raw, repeatable observation, the bedrock of modern science. He rolled balls down inclined planes to study motion, timed pendulum swings with his pulse, and turned his telescope into a truth detector. In doing so, he revealed a universe far stranger than philosophers had imagined. Mountains on the moon, phases of Venus, countless stars invisible to the naked eye. Each discovery whispered the same unsettling idea: reality doesn't care about human assumptions. The philosophical ripples of his work still touch us today. Every time a modern physicist peers through a quantum microscope or a space telescope, they're inheriting Galileo's defiance, the audacity to let nature speak for itself. His trial and house arrest remind us how costly truth can be, but his legacy is clear. Progress demands the courage to see differently. Those who dismissed his findings as optical illusions weren't just wrong about Jupiter's moons, they were clinging to a worldview that valued comfort over curiosity. Galileo's true gift wasn't the telescope itself, but the radical humility it demanded, the willingness to let the universe surprise us. Isaac Newton's apple didn't just fall, it crashed through centuries of cosmic speculation, leaving behind a universe that ticked with mechanical precision. His laws of motion transformed the heavens from a realm of divine mystery into a vast, predictable machine, where every celestial body moved according to immutable mathematical rules. Picture the cosmos as an enormous clockwork, every gear turning in perfect synchrony, from the arc of a cannonball to the orbit of distant planets. For Enlightenment thinkers, this was nothing short of revelatory. Suddenly, chaos had order. Comets weren't omens, they were equations waiting to be solved. The universe, it seemed, played by rules anyone with a quill and parchment could decode. But beneath this triumph of reason lurked an unsettling question. If the stars obey unbreakable laws, do we? Newton's clockwork cosmos didn't just explain motion, it reshaped humanity's understanding of free will. Philosophers like Pierre-Simon Laplace took the idea even further, imagining a hypothetical demon who, knowing the position and momentum of every particle in the universe, could calculate the entire future and past with perfect accuracy. In such a world, choice becomes an illusion, a flickering shadow cast by gears we can't see. The poet Alexander Pope captured the tension perfectly. Nature and nature's laws lay hid in night. God said, "Let Newton be." And all was light. Yet that very light cast long shadows over human agency. Newton himself wrestled with the implications. A devout man, he insisted that God occasionally intervened to adjust the cosmic clock, a subtle admission that pure determinism felt spiritually hollow. Meanwhile, artists and writers recoiled at the idea of a universe stripped of mystery. William Blake famously denounced Newton's single vision, painting him as a figure reducing rainbows to mere prisms, trading wonder for cold calculations. The irony, Newton's laws, for all their rigidity, became a springboard for new kinds of freedom. By proving the universe operated uniformly, they empowered scientists to experiment boldly, trusting that nature wouldn't capriciously change its rules. The legacy of Newton's clockwork universe echoes in every modern scientific leap, from spaceflight to quantum computing. Yet it also serves as a cautionary tale about the limits of human knowledge. Later revolutions, Einstein's relativity, Heisenberg's uncertainty, would prove the cosmos far less predictable than Newton dreamed. But that initial vision, for all its mechanical simplicity, taught us something profound. The universe isn't arbitrary. It speaks in patterns, and in learning to listen, we didn't lose our sense of wonder. We gave it new language. The real magic lies not in whether the cosmos is a clockwork, but in the fact we can hear it ticking at all. Einstein's universe bends, where Newton saw straight lines and absolute clocks ticking uniformly across the cosmos. Einstein revealed a reality as pliable as warm taffy, a four-dimensional fabric where space and time stretch, warp, and twist under the weight of matter and energy. Picture tossing a bowling ball onto a trampoline. The way the fabric dips and curves is precisely how planets bend space-time around themselves, creating what we feel as gravity. But here's the mind-bending twist. This isn't just about objects moving through space, it's about space and time themselves being dynamic players in the cosmic dance. When Einstein published his theory of general relativity in 1915, he didn't just correct Newton's equations, he dismantled humanity's most basic intuitions about reality. Suddenly, time wasn't a universal metronome but a personal experience. An astronaut orbiting Earth ages microseconds slower than someone on the ground, not because of some mechanical error, but because time itself flows differently where gravity's grip varies. Philosophers reeled. If time is relative, what happens to cause and effect? Could the past, present, and future exist simultaneously, like frames in a cosmic film strip waiting to be observed? Einstein's friend Michel Besso captured the existential vertigo perfectly, writing, "For us physicists, the distinction between past, present, and future is only an illusion, however persistent." This wasn't just abstract theorizing. Relativity's predictions have been confirmed with astonishing precision. From the way starlight bends around the sun during eclipses to the infinitesimal time delays caught by atomic clocks on airplanes. Even the GPS in your phone quietly corrects for relativity's effects. Ignore them, and your navigation would drift off by miles within hours. but the implications ripple far beyond technology. Einstein's work forced philosophers to confront a startling possibility. Reality might be less like a collection of objects and more like a network of relationships, where even the most fundamental properties, length, duration, mass, depend on the observer's perspective. Consider the famous twin paradox, where one twin rockets off at near light speed and returns younger than their earthbound sibling. This isn't science fiction, it's a direct consequence of spacetime's flexibility. The universe, it seems, is a stage where the very scaffolding of existence adapts to the actor's motions. Artists and writers seized on this fluidity. Salvador Dali's melting clocks in the persistence of memory aren't just surrealism, they're relativity visualized. Meanwhile, theologians debated whether Einstein's block universe, where all of time exists at once, left room for free will or divine intervention. The real revolution, though, lies in how Einstein's cosmos humbles us. Newton's universe was a majestic clockwork, predictable and detached. Einstein's is participatory, a canvas where every star, planet, and human observer subtly alters the texture of reality itself. When we look up at the night sky today, we're not just seeing distant lights, we're glimpsing a cosmic tapestry where space remembers the weight of galaxies, and time carries the imprint of every moment that ever was. Relativity didn't just change how we calculate orbits, it redefined what it means to exist within the universe's embrace. If Newton's universe was a clockwork and Einstein's a flexible fabric, then the quantum realm is a hall of mirrors, a place where particles exist in ghostly superpositions, being everywhere and nowhere until the moment you look. Picture an electron not as a tiny ball orbiting an atom's nucleus, but as a shimmering cloud of possibilities, its location undefined until measurement forces it to choose. This isn't just theoretical oddness, it's the foundation of modern technology, from lasers to smartphones. Yet beneath the equations lies a philosophical bombshell. At its core, reality might not exist independently of our observation. Take the famous double-slit experiment, where particles like photons or electrons are fired at a barrier with two openings. When unobserved, they behave like waves, creating an interference pattern on the detector screen, as if each particle passes through both slits simultaneously. But the instant scientists place a measuring device to track which slit a particle takes, the wave pattern collapses. The particles decide to behave like discrete objects. It's as if the universe is shy, changing its behavior when watched too closely. Nobel physicist Niels Bohr summarized this paradox bluntly. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. This observer effect ripples far beyond physics labs. It resurrects ancient philosophical debates about whether the moon exists when no one's looking. Questions once the domain of idealists like Bishop Berkeley. Quantum mechanics doesn't necessarily say consciousness creates reality, but it undeniably ties measurement to outcome in ways that unsettle our classical intuitions. Even Einstein resisted these implications, insisting God does not play dice with the universe. Yet decades of experiments, from quantum entanglement tests to delayed choice setups, keep confirming the theory's bizarre predictions. Particles separated by light years can instantaneously affect each other's states, defying locality. Time itself seems malleable. In the quantum world, an effect can sometimes precede its cause. The implications are staggering. If observation shapes reality at the smallest scales, does that mean the universe requires observers to fully exist? Some interpretations, like the Copenhagen school, suggest particles only settle into definite states when interacting with a larger system, a slippery slope toward privileging consciousness. Others, like the many worlds hypothesis, propose that every quantum possibility branches into parallel universes, rendering the observer's role less mystical but no less mind-bending. Meanwhile, pragmatists focus on the math's predictive power, dismissing metaphysics altogether. Artists and writers have seized on these ideas, from Borges' labyrinthine stories to films like The Matrix, where reality is a collective projection. But the deeper lesson might be epistemological. Quantum mechanics exposes the limits of human perception. Just as Copernicus showed Earth isn't the center of the cosmos, quantum theory suggests our senses and instruments can't access reality's true nature, only the slice that interacts with us. The universe, it seems, is less a static stage and more an ongoing negotiation between the seen and the seer. Every time you check your phone's GPS or stream a video, you're harnessing this quantum weirdness, proving that the most counterintuitive science can become mundane yet never less miraculous. The cosmos sprawls across nearly 100 billion light-years, dotted with 2 trillion galaxies, each home to hundreds of billions of stars. Statistically, the numbers scream that we should be drowning in alien neighbors, so why does the universe feel so silent? This is the heart of the Fermi Paradox, named for physicist Enrico Fermi, who famously asked over lunch in 1950, "Where is everybody?" On paper, the math is undeniable. Even if only 1 in a million stars hosts a civilization, there should still be millions out there. Yet our radio telescopes hear only static, our telescopes see no megastructures, and our planet remains curiously undisturbed. The paradox isn't just about counting aliens, it's about confronting the eerie possibility that something fundamental, maybe even sinister, is missing from our equations. Consider the sheer timescales at play. Earth is 4.5 billion years old, but the universe has been forming stars for over 13 billion. If just one civilization arose a few million years before us, a blink in cosmic terms, they could have colonized the galaxy by now. Imagine a culture mastering interstellar travel just as early humans were discovering fire. They'd have had epochs to build Dyson spheres around stars, launch self-replicating probes, or rearrange constellations as they pleased. The fact that we see none of this suggests a chilling filter, some near inescapable hurdle that prevents civilizations from reaching the stars or surviving long enough to try. That's where the philosophical weight crashes in. The Great Filter theory proposes that life must overcome some nearly impossible barrier, and we don't know whether it's behind or ahead of us. If the filter is in our past, say, the improbable jump from single-celled to multicellular life, then we might truly be among the galaxy's rare success stories. But if it looms ahead, nuclear war, climate collapse, rogue AI, then every technological civilization might unknowingly be building its own extinction. The silence of the cosmos could be a tombstone, not an empty nursery, yet there are hopeful interpretations too. Maybe advanced civilizations transcend physical exploration, uploading their minds into quantum simulations or retreating into black hole computers. Perhaps they're everywhere but deliberately hiding, following some cosmic version of the Prime Directive. Or, as astronomer Carl Sagan mused, maybe the distances are simply too vast and every civilization is an island, separated by oceans of spacetime too wide to cross. The paradox forces us to re-examine our assumptions about intelligence itself. We hunt for radio signals because that's how we communicate, but what if alien minds share thoughts through neutrino bursts or gravitational waves? We look for Dyson spheres because we imagine energy-hungry civilizations, but what if they've tapped into dark matter or learned to live with less? The universe's silence might not mean no one's out there, just that we're listening for the wrong things, like ancient sailors scanning the horizon for wooden ships while submarines glide unseen beneath them. Ultimately, the Fermi Paradox holds up a mirror to our own fragility and audacity. In a trillion-star universe, the mere fact that we're here to ask the question is either a statistical fluke or a clue to something profound. Every time a Mars rover drills into red rocks or the James Webb Telescope peers at exoplanet atmospheres, we're not just hunting for microbes or methane. We're probing the boundaries of existence itself, testing whether life is a cosmic accident or the universe's most spectacular secret, waiting to be whispered across the light years. Dark matter is the universe's best-kept secret, a cosmic ghost that refuses to show itself. We know it's there because galaxies spin too fast for the visible matter holding them together, like a merry-go-round whirling so violently that its chains should snap. Yet when we reach out to grasp the invisible hand keeping everything in place, our fingers close around nothing. This isn't just a scientific puzzle, it's a philosophical reckoning. How do we study something that doesn't interact with light, doesn't clump like normal matter, and might not even be made of particles as we understand them? The more we learn, the more we realize how little we truly know. Consider the evidence. When astronomers observe distant galaxy clusters, they see light bending around vast, empty regions, as if space itself is haunted by unseen mass. These gravitational mirages, called Einstein rings, reveal dark matter's presence the way a shadow reveals a hidden figure. Yet despite decades of hunting, from deep underground labs searching for hypothetical WIMP to space telescopes mapping its gravitational fingerprints, dark matter remains stubbornly elusive. It's as if the universe is playing a cosmic game of hide and seek, and we're still learning the rules. This isn't just a gap in our knowledge, it's a chasm. Modern physics rests on the idea that observation and experimentation can unveil nature's secrets. But what happens when nature hides its most fundamental components? Dark matter forces us to confront the uncomfortable possibility that some truths might lie beyond human perception. Philosophers of science call this the unobservability problem, the idea that certain aspects of reality might be inherently inaccessible to us, no matter how advanced our tools become. It's like trying to describe an elephant based solely on its silhouette, never knowing its texture, weight, or warmth. The implications ripple far beyond astronomy. If most of the universe is invisible to us, how can we trust our understanding of anything? Ancient cultures once believed the night sky was a tapestry of gods and myths. Today, we swap those stories for equations and models. But dark matter reminds us that even our most sophisticated theories are provisional maps of a territory we've only glimpsed. The German philosopher Immanuel Kant argued that we perceive reality through the lens of our own mental frameworks, never accessing the thing in itself. Dark matter might be the ultimate embodiment of that idea, a reminder that the universe owes us no obligation to make sense, yet there's a strange beauty in this uncertainty. The hunt for dark matter has sparked some of the most creative science in generations. Researchers are probing actions, sterile neutrinos, and even primordial black holes from the dawn of time. Others wonder if we've misunderstood gravity itself, proposing radical theories like modified Newtonian dynamics that rewrite the cosmic rulebook. Every dead end sparks new questions, and every failed detection refines the search. In a way, dark matter has become the ultimate muse, pushing us to rethink not just the composition of the cosmos, but the very nature of discovery. Perhaps the most humbling lesson is this: the universe doesn't care about our hunger for answers. It will withhold its secrets as long as it pleases. But in that withholding, it gifts us something equally valuable: the thrill of the unknown, the joy of chasing shadows, and the humility to admit that some mysteries might outlast us. After all, a universe that could be fully understood would be smaller than the minds trying to comprehend it. And where's the wonder in that? Black holes are the universe's most enigmatic paradoxes, regions where gravity becomes so overpowering that not even light can escape, and time itself distorts into something unrecognizable. Picture standing at the edge of one, watching a clock fall toward its event horizon. From your perspective, its hands would slow, then freeze, as if time had simply stopped. Yet from the clock's point of view, it would plunge relentlessly forward, torn apart by tidal forces in what physicists call spaghettification. This isn't just science fiction, It's the stark reality of Einstein's general relativity pushed to its extremes. Black holes don't just bend space-time, they shatter our intuitive understanding of cause and effect, leaving us to wonder what exactly happens to time, matter, and even information when they cross that invisible threshold. The strangeness doesn't stop there. According to quantum mechanics, information can never truly be destroyed. It might get scrambled, but it should always be recoverable in principle. Yet black holes seem to violate this rule. When matter falls in, it's compressed into an infinitely dense singularity, leaving no trace of its original structure. Stephen Hawking's work revealed that black holes slowly evaporate over eons, radiating away energy in what we now call Hawking radiation. But here's the catch: this radiation appears random, carrying no information about what fell in. That creates the infamous black hole information paradox, a clash between relativity and quantum theory that has physicists locked in debate. Is information truly lost forever, or is it somehow encoded in the radiation or hidden in some deeper layer of reality? These questions aren't just academic, they force us to confront the fundamental nature of reality itself. Some theorists, like Leonard Susskind, propose the holographic principle, the idea that all the information inside a black hole might be preserved on its two-dimensional surface, like a cosmic thumb drive storing data in ways we don't yet understand. Others, like Roger Penrose, suggest that black holes might be portals to entirely new universes where the laws of physics reset. Meanwhile, experiments with analog black holes in labs, using sound waves or ultra-cold fluids, are testing these ideas in miniature, offering glimpses into how space-time might behave under such extreme conditions. Philosophically, black holes challenge our very notion of existence. If time stops at the event horizon, does that mean the fate of anything falling in is suspended forever, like a fly trapped in amber? Or does it mean that, from the universe's perspective, the object never actually crosses, existing instead as a frozen smear on the boundary? These aren't just thought experiments, they're windows into the limits of human comprehension. Artists and writers have long been fascinated by black holes as metaphors for oblivion, for transformation, even for the unknowable mysteries of consciousness. Yet perhaps the most profound lesson black holes teach us is humility. They remind us that the universe isn't obligated to conform to our expectations. For all our equations and theories, these cosmic anomalies stand as gatekeepers to realms where logic as we know it fails. Every time astronomers capture an image of a black hole's shadow or detect gravitational waves from their collisions, we're not just collecting data, we're peering into the abyss, daring to ask questions that might have no answers. And in that asking, we touch the edge of something far grander than ourselves, the raw, unfiltered mystery of existence. Imagine discovering that every choice you've ever made, from what you ate for breakfast to the career you pursued, played out differently in another reality. Somewhere, a version of you became an astronaut while another never left their hometown. This isn't science fiction. It's the Multiverse Hypothesis, one of the most provocative ideas in modern cosmology. At its core lies a radical proposition. Our universe might be just one bubble in an infinite cosmic foam, each with its own unique laws of physics. Some universes could have stronger gravity, making stars burn out in moments. Others might lack electromagnetism, leaving atoms unable to form molecules. In this vast ensemble, every possible configuration of reality could exist somewhere, including versions where you never existed at all. The math behind this idea isn't pure speculation. When physicists study the early universe, they find clues suggesting spacetime underwent a rapid expansion called inflation. Some theories propose that inflation never truly stopped. It just paused in our pocket of reality while continuing endlessly elsewhere, birthing new universes like soap bubbles in a sink. String theory adds another layer, with its 10 or 11 dimensions curled into shapes that could manifest entirely different physics. Even quantum mechanics hints at branching realities through the many worlds interpretation, where every quantum decision spawns parallel timelines. The evidence is indirect, like footprints in cosmic background radiation, but the implications are staggering. Philosophically, the multiverse forces us to confront what it means to be unique. If countless versions of Earth exist, complete with doppelgangers making different choices, does any single life hold intrinsic meaning? Some thinkers argue this actually elevates our significance. Every decision creates new branches of reality, making each moment a nexus of infinite possibilities. Others find it unsettling, as if humanity's story gets diluted across an endless array of alternate narratives. Theologians debate whether a multiverse requires a multiverse maker, while ethicists ponder whether we bear responsibility for the suffering of our other selves in harsher realities. Consider probability in such a cosmos. With infinite universes, even the most unlikely events must occur somewhere. A planet identical to Earth might exist where dinosaurs never went extinct or where Rome conquered the Americas. Statistically, there should even be universes where the laws of physics permit magic or perpetual motion machines. This Anthropic Principle offers one explanation for why our universe appears fine-tuned for life. If every possible set of physical constants exists, we naturally find ourselves in one where life is possible, no matter how improbable. Yet the multiverse remains contentious. Critics argue it's untestable by definition. If other universes are forever beyond our observational reach, does the hypothesis cross from science into metaphysics? Supporters counter that subtle fingerprints might linger, like cold spots in the cosmic microwave background where bubble universes collided with ours. Future telescopes or particle accelerators could uncover evidence hiding in higher dimensions or quantum entanglement patterns. What makes the multiverse so captivating isn't just the science, but how it reshapes our existential coordinates. Whether it's ultimately proven or not, the idea stretches our imagination beyond the single universe we see, inviting us to ponder realities where black holes are doorways. Dark matter is just ordinary matter in a different dimensional orientation, and every crossroads in your life leads not to one destination, but to countless parallel journeys unfolding across the cosmic tapestry. In that sense, the multiverse isn't just a theory, it's the ultimate thought experiment, challenging us to redefine what real even means. What if the universe isn't just hospitable to life by accident, but because it couldn't be any other way? This is the spine-tingling question at the heart of the Anthropic Principle. Consider the cosmic constants that make existence possible. If gravity were slightly stronger, stars would burn out too quickly for planets to form. If the weak nuclear force were a fraction weaker, hydrogen wouldn't fuse into the heavier elements that build our bodies. These numbers aren't just arbitrary, they're precision tuned to an almost impossible degree, like a lock with a billion combinations that opens only when every dial lands exactly right. Philosophers and physicists have wrestled with this fine-tuning for decades. On one side, proponents of the strong anthropic principle argue the universe must produce observers like us, implying some form of inevitability, even design. Cosmologist Brandon Carter, who coined the term in 1974, compared it to a fisherman marveling at how perfectly the lake's depth matches his net's length, only to realize he couldn't have caught fish any other way. In this view, the laws of physics aren't arbitrary, they're constrained by the necessity of creating conscious beings to observe them. Yet skeptics counter with the weak anthropic principle, a humbler interpretation. It suggests we shouldn't be surprised to find ourselves in a life-permitting universe because we couldn't exist in one that wasn't. Imagine a puddle waking up and marveling at how perfectly its hole fits its shape. The hole wasn't made for the puddle simply conformed to what was there. Applied cosmically, this perspective frames fine-tuning as observational selection bias. Of course, we find ourselves in the rare slice of reality where conditions allow our existence. We're the ones doing the looking. The debate intensifies when paired with the multiverse theory. If infinite universes bubble into existence with random physical constants, most would be sterile voids where atoms never bond or gravity crushes all structure. But statistically, a few would hit the jackpot, and we'd inevitably find ourselves in one. This cosmic lottery explanation dodges the need for a designer, but at a cost. It replaces one mystery, why this universe, with another, why these multiverse rules. Theological interpretations add another layer. Some see fine-tuning as evidence of a cosmic architect, while others, like physicist Paul Davies, propose a self-explaining universe where consciousness is woven into the fabric of reality. Meanwhile, critics like Richard Dawkins dismiss design arguments as the ultimate Boeing 747 gambit, invoking an even more complex creator to explain complexity. At its core, the Anthropic Principle exposes how deeply science and philosophy intertwine when we stare into the cosmos. Every measurement of a fundamental constant, every simulation of alternate physics, becomes a mirror reflecting our own existential questions. Whether through multiverses, metaphysics, or sheer cosmic luck, the universe whispers a tantalizing possibility that the very act of observation might be written into its deepest laws. In seeking answers, we're not just studying the stars, we're deciphering what it means to be a fleeting flicker of awareness in an unfathomably vast, yet strangely hospitable cosmos. Think about the delicate balance that makes life possible, like a cosmic tightrope walker, maintaining perfect equilibrium on a thread thinner than a spider's silk. If the strength of the strong nuclear force were just 2% weaker, protons wouldn't bind together, leaving the universe as a lifeless sea of hydrogen. If the cosmological constant, the mysterious energy accelerating the universe's expansion, were slightly larger, galaxies would have ripped apart before life could emerge. The numbers governing our reality aren't just arbitrary. They're threaded together with a precision that defies randomness, as if the universe itself had a blueprint. This eerie perfection has sparked one of the most profound debates in modern thought. Is the cosmos fine-tuned because it was designed to be, or are we simply the lucky winners of a multiverse lottery? Theologians point to the exactness of these constants as evidence of intentionality, a cosmic architect carefully calibrating the dials of existence. Philosopher Richard Swinburne compares it to a machine with countless interdependent parts, each adjusted to perfection. The odds of such harmony emerging by chance, he argues, are so infinitesimal that design becomes the more plausible explanation, yet scientists offer a different lens. In the multiverse scenario, our universe is just one page in an infinite library, each volume with its own set of physical laws. Most would be gibberish universes collapsing instantly or devoid of structure, but statistically, a few would land on the precise combination that permits life. We find ourselves in one not because it was chosen, but because we couldn't observe the others. Theoretical physicist Sean Carroll frames it like this: you don't marvel at being dealt a royal flush if you've been playing poker for 10 billion years. The tension between these views reveals a deeper question about causality. Does the universe's apparent fine-tuning imply a why, or can it be reduced to a how? Ancient Stoics saw purpose in the stars' motions. Modern string theorists speak of landscape vacuums spawning universes. Both are grappling with the same awe, but through different vocabularies. Even the secular can't escape the whisper of teleology, the sense that the cosmos is oriented toward something, whether it's complexity, consciousness, or something beyond our current comprehension. Consider carbon-based life, the universe's most intricate pattern. For carbon to form, stars must forge helium into beryllium, then fuse it with another helium nucleus in a precise three-step dance. The resonance levels of these elements align with freakish perfection, a coincidence so unlikely that physicist Fred Hoyle famously quipped it felt like a put-up job. Was this mere happenstance, or does it hint at something more? The answer you favor says less about the universe and more about your philosophy, whether you see existence as a closed equation or an open question. Critics argue that invoking design is a God of the gaps fallacy, filling scientific unknowns with divine explanations. But proponents counter that fine-tuning isn't about gaps, it's about the eerie coherence of the known. The debate may never be settled empirically, but its value lies in the tension itself. It forces us to confront whether the universe is ultimately for something, or if purpose is just a story we tell to make sense of the dark. At the intersection of these ideas, one truth remains: the cosmos is far stranger than we imagined, and our place in it far more precarious. Whether by intention or accident, we're here, conscious fragments of a universe that seems, against all odds, to welcome us. And that realization, more than any theory, might be the most profound tuning of all. What if everything you've ever known, the warmth of sunlight, the taste of strawberries, even the ache of heartbreak, was just lines of code in some advanced civilization's computer? The simulation argument isn't science fiction. It's a serious hypothesis debated by philosophers and physicists alike. At its core lies a simple but unsettling premise: if a civilization could create simulations indistinguishable from reality, and if they had any reason to do so, the odds suggest we're more likely to be inside one of those simulations than in the original, base reality. Think about how far human technology has come in just a century, from hand-cranked calculators to virtual worlds where millions interact daily. Now imagine a civilization 1,000 or 1,000,000 years more advanced. Their computational power might make creating entire universes as trivial as we find building video games. Oxford philosopher Nick Bostrom formalized this idea in 2003, arguing that at least one of three propositions must be true. Either civilizations like ours always go extinct before reaching simulation capability, they choose not to run ancestor simulations, or we're almost certainly living in one. Given how many simulations such a civilization could run, the math tilts heavily toward the third option. Quantum mechanics adds eerie weight to this speculation. At the subatomic level, particles exist in fuzzy superpositions until measured behavior that seems oddly like a video game, rendering only what the player observes to save processing power. Even the pixelated nature of reality, where Planck length sets a minimum resolution to spacetime, feels suspiciously like a cosmic rendering limit. Some researchers, like Silicon Valley entrepreneur Elon Musk, argue these quirks might be glitches in the simulation's code. But proving or disproving the theory is fraught with paradoxes. If the simulators don't want us to know, they could easily erase any evidence. Some scientists have proposed looking for computational shortcuts like rounding errors in high-energy physics or anomalies in cosmic ray distributions that might reveal the universe's source code. Others suggest attempting to hack the simulation by creating our own mini-universes in labs. Yet even these tests might be rigged by higher-level programmers. Philosophically, the simulation hypothesis resurrects age-old questions about the nature of reality. Plato's cave allegory depicted humans as prisoners mistaking shadows for substance. 17th century thinker René Descartes worried an evil demon might be deceiving his senses. Now, instead of demons or caves, we grapple with quantum processors and nested simulations. The implications ripple through ethics too. If suffering is just data in a machine, does it lose meaning, or does it become more tragic knowing pain might be someone's entertainment? Critics counter that the theory is unfalsifiable, a modern-day solipsism that explains everything and nothing. Physicist Sabine Hossenfelder compares it to religion, comforting in its suggestion that someone's in control but ultimately untestable. Yet, even if we can't confirm the simulation hypothesis, its value lies in how it stretches our thinking. Like Copernicus displacing Earth from the universe's center, the idea forces us to question not just where we are, but what we even means in a cosmos where consciousness could be as transferable as a software update. Whether metaphor or literal truth, the simulation argument holds up a mirror to our insecurities and aspirations. It asks what remains of human dignity if we're just avatars in an alien child's game, and what breathtaking possibilities open if we one day learn to reprogram the rules. After all, if this is a simulation, then reality is far more malleable than we dared dream. And if it's not, the mere fact that we can imagine such a scenario speaks volumes about the universe's most surprising feature, minds capable of questioning their own existence. Time's arrow flies in one direction only like an hourglass that never flips itself over. We remember the past but not the future. Eggs scramble but never unscramble. Stars burn out but never reignite. This relentless forward march is governed by entropy, the universe's tendency toward disorder, as described by the second law of thermodynamics. But here's the cosmic riddle. If entropy always increases, why did the universe start with such astonishingly low entropy in the first place? Imagine finding a library where every book begins neatly alphabetized, only to watch it descend into chaos over time. The real mystery isn't the mess, it's the inexplicable initial order. Digging deeper reveals how bizarre this starting point truly was. The early universe was almost perfectly smooth, a hot soup of particles distributed with near-uniform precision, a state so improbably organized that physicist Sir Arthur Eddington compared it to balancing a pencil on its tip. From there, entropy had nowhere to go but up, creating the arrow of time we experience. But why did the cosmic story begin with such an unnatural condition? Some theorists, like Sean Carroll, suggest our universe might be a fluctuation in a far larger multiverse, where rare pockets temporarily dip into low entropy like bubbles forming in boiling water. Others, like Roger Penrose, propose that the Big Bang's pristine order hints at a cyclical cosmos, where each new universe inherits a reset entropy from the death of its predecessor. The implications stretch beyond physics into the heart of human experience. If time's flow emerges from entropy's rise, does that mean free will is an illusion, just particles obeying thermodynamic inevitability? Philosophers split on this question. Determinists argue that every thought and action is preordained by the initial low entropy state, playing out like dominoes falling. But compatibilists counter that free will can coexist with physical laws, just as a river's flow follows gravity's pull while still carving unique paths. Meanwhile, quantum mechanics adds another layer. At microscopic scales, particles seem to make genuine random choices, suggesting the universe might have built-in wiggle room for spontaneity. Causality itself gets tangled in time's arrow. We're used to causes preceding effects, but some equations in physics work equally well backward. The difference, as Nobel laureate Ilya Prigogine noted, is that irreversible processes like milk mixing into coffee create memory in the universe, etching the direction of time into reality. This irreversibility might even be the key to consciousness. Neuroscientist Giulio Tononi theorizes that our brains rely on causal structures that only make sense in an entropy-driven timeline, meaning subjective experience could be intertwined with thermodynamics. Perhaps the most humbling realization is how much we take time's arrow for granted. We're like fish who have never questioned water, oblivious to the fact that our entire existence, from aging to memory to the very concept of progress, depends on this cosmic asymmetry. The universe could have been born in high entropy, a featureless equilibrium where nothing changes and nothing matters. Instead, we find ourselves in a fleeting golden era where structure and complexity bloom, giving rise to galaxies, life, and minds capable of pondering why time flows at all. In that sense, every ticking clock is a reminder of our improbable gift, a universe with a past, a present, and the tantalizing possibility of a future still unwritten. Why does the soft glow of a sunset feel warm and alive, while a computer processing the same wavelengths of light experiences nothing at all? This gap between physical processes and conscious experience is what philosopher David Chalmers famously dubbed the hard problem of consciousness, a puzzle so deep it reverberates through both neuroscience and cosmology. At its heart lies a simple but staggering question. How can the electrical storms of neurons, the chemical ballet of synapses, give rise to the vivid, private world of thoughts, colors, and emotions that each of us inhabits? Consider the sheer oddness of subjective experience. A brain scanner might map the neural fireworks that occur when you taste chocolate, but no scan can capture the rich, creamy sweetness you actually perceive. This qualitative aspect, what philosophers call qualia, seems to float above the machinery of the brain like smoke above a fire, present but irreducible to mere physics. Some argue this gap exposes a fundamental limitation in our materialist worldview. If consciousness can't be fully explained by atoms and forces, might it be as foundational to reality as space and time? This is where cosmology enters the conversation. Certain interpretations of quantum mechanics, like the von Neumann-Wigner hypothesis, propose that consciousness isn't just a bystander in the universe, it's an active participant. In the famous double-slit experiment, particles behave as waves until observed, collapsing into definite states only when measured. But what counts as a measurement? Some theorists suggest it's not the detector, but the conscious awareness behind it that seals reality into place. It's as if the universe remains a haze of possibilities until a mind looks at it, like a dream that solidifies only when someone wakes. Of course, not all scientists buy into this radical view. Critics argue it's a modern version of solipsism, placing unwarranted importance on human observation. They point out that quantum decoherence interaction with the environment can collapse wave functions without any conscious observer, yet the alternative isn't much less strange. If consciousness emerges purely from matter, then at some point in the evolutionary chain, lifeless atoms must have sparked into subjective awareness, a transition as mystifying as turning sand into symphonies. The implications spiral outward like galaxies. If consciousness is woven into the cosmos, might stars and black holes harbor some dim form of it? Panpsychists argue that even electrons could possess a whisper of experience, with complex minds like ours arising from their collective hum. Others, like physicist Sir Roger Penrose, speculate that quantum processes in microtubules within brain cells might bridge the gap between physics and feeling. Meanwhile, the simulation hypothesis flips the script entirely. What if our consciousness is just code in some vast cosmic computer? Perhaps the most humbling takeaway is how little we truly understand. After centuries of dissecting brains and charting neurons, the hard problem remains untouched, a reminder that the universe's greatest mysteries might not be out among the stars, but right here behind our own eyes. Every time you savor a melody, wince at pain, or lose yourself in a memory, you're experiencing something science can't yet explain. The alchemy that transforms electrical pulses into the technicolor movie of lived experience. And that mystery might hold the key to realities far beyond our own. Imagine a tiny microbe, no larger than a speck of dust, hitching a ride inside a comet as it streaks through the frigid void of space. After millions of years frozen in cosmic ice, the comet crashes into a young, water-rich planet. And suddenly, that dormant microbe wakes up, seeding life in a new world. This is the heart of Panspermia, the audacious idea that life doesn't originate on planets but travels between them, spreading like spores on the interstellar wind. It's a theory that turns our Earth-centric view of biology upside down, suggesting that life might not be a rare accident confined to our pale blue dot, but a cosmic inevitability as persistent and widespread as stardust itself. The evidence, while circumstantial, is tantalizing. Meteorites like the famous Murchison specimen, which landed in Australia in 1969, contain amino acids, the building blocks of proteins, as well as sugars and even nucleobases, the raw materials of DNA. These organic compounds aren't just random. Some have a molecular handedness or chirality that mirrors the bias seen in earthly life. Then there's the survivalist resilience of certain extremophiles bacteria like Deinococcus radiodurans, which can endure the vacuum of space, lethal radiation, and extreme temperatures. If such hardy organisms exist on Earth, why couldn't they survive an interstellar journey encased in a protective layer of rock or ice? But panspermia isn't just about microbes catching cosmic rides. It raises profound philosophical questions about life's origins and purpose. If life didn't begin here, where and when did it start? Some theories suggest it could be older than Earth itself, perhaps brewing in the warm, watery plumes of ancient comets or around the volcanic vents of long-dead exoplanets. Others propose that life might have begun near the center of the galaxy, where heavier elements necessary for biochemistry were more abundant, then spread outward over billions of years. This shifts the narrative from life as a localized phenomenon to something more like a galactic infection, pulsing through the cosmos in waves. The implications ripple outward. If life is universal, then the distinction between alien and native biology blurs. We might all share a common cosmic ancestor, making the search for extraterrestrial life less about finding strangers and more about reconnecting with distant relatives. It also reframes the Fermi Paradox. Instead of asking why we haven't found life, we might wonder if we're just latecomers to a party that started eons ago, with the remnants of ancient civilizations already dissolved into the stellar background. Philosophically, panspermia forces us to confront the possibility that life isn't a fluke. It's a fundamental feature of the universe, as natural as gravity or light. Just as stars forge heavy elements and supernovae scatter them across the cosmos, life might be part of the universe's grand chemistry, an emergent property as inevitable as crystallization or combustion. Some thinkers, like astronomer Fred Hoyle, took this idea even further, suggesting that life could be a kind of cosmic immune response, a way for the universe to evolve complexity and perhaps even awareness. Yet skeptics counter that panspermia merely kicks the can down the road. It doesn't explain how life began, only how it might spread. And without direct evidence, like finding a living organism in a meteorite or detecting DNA like molecules in interstellar space, the theory remains a compelling but unproven hypothesis. Still, the mere possibility reshapes how we see our place in the cosmos. If life is truly a traveler, then Earth isn't a solitary oasis, it's a way station in an endless journey, one tiny node in a vast, interconnected web of living worlds. So the next time you gaze up at the stars, consider this. The same cosmic currents that carry comets and asteroids might also be ferrying the seeds of life, silently weaving a tapestry of biology across the galaxy. Whether panspermia is proven or not, it invites us to see life not as something that happens on planets, but to planets, a force as boundless and enduring as the universe itself. For centuries, humanity saw life as a singular miracle, a flickering candle in the cosmic dark. But astrobiology has turned that assumption on its head, forcing us to ask, what truly makes something alive? Is it the ability to metabolize, to reproduce, to adapt? Or is life something more elusive, a pattern of complexity, a whisper of information persisting against entropy's tide? These aren't just scientific questions, they're philosophical earthquakes shaking the foundations of how we see ourselves. Consider Viking landers in 1976, scraping Martian soil for signs of metabolism. Their ambiguous results revealed a deeper truth. We didn't even know what to look for. Earth's biology relies on DNA, water, and carbon, but what if life elsewhere dances to a different chemical rhythm? Imagine organisms thriving in Titan's methane lakes, their cells built from lipids instead of proteins, or silicon-based creatures pulsing in the superheated vents of distant exoplanets. The more we search, the more our terrestrial definitions crumble. This search does more than expand the catalogue of life. It holds up a mirror to our own existence. Finding even a single microbe on Europa's icy shores would prove life isn't a fluke of Earth's chemistry but a cosmic imperative. Suddenly, the tree of life might have roots stretching across light years, its branches woven through the galaxy. Would that realization humble us or exhilarate us? History offers clues. When Copernicus displaced Earth from the universe's center, it sparked not despair but revolution, a flowering of art, science, and philosophy fueled by newfound humility. Astrobiology could trigger a similar awakening, replacing loneliness with connection. Yet some fear the opposite, that discovering simple life elsewhere might strip humanity of its specialness. But this misses a profound truth. Rarity doesn't confer meaning. A diamond is precious because we value its sparkle, not because it's alone in the universe. Likewise, our consciousness, creativity, and capacity for wonder don't diminish if shared, they gain context. The real revelation might be that life isn't a solitary accident, but the universe's way of understanding itself, with each civilization a unique perspective in a grand cosmic dialogue. Astrobiologists now hunt for biosignatures in exoplanet atmospheres, oxygen, methane, even synthetic pollutants hinting at intelligence. But the deeper quest is for a theory of life robust enough to recognize its alien forms. Some researchers model life as a self-sustaining system far from equilibrium, others as information processing against chaos. Each framework stretches our imagination, revealing how narrow our current lens might be. Perhaps the most startling possibility is that we're searching for something we can't yet conceive. Life might not always look active or even material. It could exist as slow chemical waves in planetary crusts or as fleeting electromagnetic patterns in nebulas. The universe is stranger than fiction. Why wouldn't its biology be too? In the end, astrobiology's greatest gift isn't answers but better questions. It teaches us that life isn't a checkbox but a spectrum, and that our definitions are just the first stammerings of a much longer conversation. Whether we find neighbors in the cosmos or not, the search itself reshapes what it means to be alive, not as solitary stardust, but as the universe's way of waking up and whispering, "I am here." The dream of walking on Martian soil or gazing at Earth from a lunar colony thrills the imagination, but it forces us to confront an uncomfortable truth. We may be on the verge of becoming interplanetary gardeners, sowing life where none existed before. Picture this: a single bacteria-laden spacecraft landing on Mars could irrevocably change the planet's pristine environment, blurring the line between exploration and contamination. This isn't just about scientific purity, it's a philosophical crossroads. Do we have the right to impose Earth's biology on another world, or does the universe operate on a finders-keepers logic where whoever arrives first dictates the rules? Consider the lessons from Earth's own history. When European explorers introduced rabbits to Australia or rats to remote islands, the ecological domino effects were catastrophic. Now imagine scaling that up to an entire planet. Mars might seem barren, but what if subterranean microbes, organisms we haven't even detected yet, are clinging to survival in briny pockets beneath the surface? By introducing Earth's hardy extremophiles, we could unwittingly trigger an extinction event on a planetary scale, erasing the very alien life we seek to study. Astrobiologists call this the forward contamination dilemma, and it's not just hypothetical. NASA's Perseverance rover was sterilized with meticulous care, but human settlers won't have that luxury. Every breath, every footprint could carry irreversible consequences, yet the ethical web stretches further. If we terraform Mars, melting its ice caps to create oceans, thickening its atmosphere to trap heat, are we playing creator or vandal? Some argue that lifeless worlds are inert matter, ripe for reshaping like clay. Others counter that celestial bodies have intrinsic value, their untouched landscapes holding scientific and even spiritual significance. The philosopher Robert Sparrow likens terraforming to the colonial mindset of terra nullius, where land is deemed empty simply because its inhabitants are unrecognizable to the conquerors. Indigenous cultures on Earth have long revered mountains and rivers as sacred. Might future generations view the Valles Marineris or Olympus Mons with similar reverence? Then there's the question of responsibility to life itself. If we're the only known sentient beings in the cosmos, does that grant us a duty to spread life as a cosmic safeguard? The biocentric view holds that life, in any form, is the universe's highest value, and seeding it elsewhere is a moral imperative, especially with Earth facing climate crises and asteroid threats. Futurists like Elon Musk frame Mars colonization as a backup drive for humanity, a hedge against planetary disaster. But this raises another quandary. If we're preserving Earth's biology, are we obligated to replicate its diversity? A Mars domed with only humans, wheat, and lab-grown meat would be a genetic monoculture stripped of rainforests, corals, and the symphony of species that make Earth vibrant. The stakes soar higher when we consider artificial life. Synthetic biologists might one day design organisms tailored for alien environments, algae that exhale oxygen in Venus's clouds, or nanobots that reshape asteroid regolith into habitable soil. These creations could blur the definition of natural life, challenging our ethical frameworks. If we engineer a microbe to thrive on Europa's ice, is it still Earth life or something new entirely? And who gets to decide? Scientists, corporations, governments, or some fledgling interplanetary ethics council? At its core, space colonization forces us to confront our self-image. Are we stewards of life, shepherds guiding it gently across the stars? Or are we a force of nature ourselves, as indifferent to cosmic consequences as a meteor impact? The answers will shape not just our future, but the universe's. Every decision, from the bacteria on our boots to the atmospheric generators we switch on, echoes with a deeper question. What kind of ancestors do we want to be for the civilizations that might one day call the stars home? The cosmos isn't just a new frontier, it's a mirror reflecting back our deepest values and contradictions, and what we see might determine whether we're destined to be cosmic gardeners or cosmic locusts. A speck of dust drifting through the void, that's all Earth would be to a passing asteroid or the shockwave of a nearby supernova. The cosmic scales of disaster are humbling. A single gamma-ray burst, a beam of energy brighter than 1,000,000 galaxies, could strip our atmosphere bare from thousands of light years away, turning the sky into a death sentence. These aren't doomsday fantasies, they're calculable probabilities written into the universe's ledger. Astronomers track over 30,000 near-Earth objects, some as wide as mountains, any one of which could rewrite human history in an instant. And yet, for all our vigilance, we're still just learning to read the cosmos's warning signs. This vulnerability forces a radical shift in perspective. If life is rare or worse, alone, then humanity's survival isn't just a local concern, it's a cosmic imperative. Think of Earth's biosphere as a flickering candle in a windstorm, sheltering not just our stories and struggles, but perhaps the universe's only chance to know itself. The ethical stakes couldn't be higher. Philosopher Nick Bostrom frames this as astronomical waste. Every premature human extinction represents an unfathomable loss of potential futures, art, and discovery that might have spanned millennia or even galaxies. But here's the paradox. To survive cosmic threats, we must first overcome our own. nuclear arsenals, climate tipping points, and unaligned artificial intelligence loom larger in the near term than any asteroid. It's as if we're passengers on a lifeboat, bickering over supplies while ignoring the storm clouds gathering on the horizon. The challenge isn't just technological, it's psychological. Our brains evolved to prioritize immediate dangers like predators or harsh winters, not slow-moving calamities or abstract celestial hazards. Bridging that cognitive gap requires something unprecedented. A species-wide paradigm shift toward long-termism, the ethical view that future lives matter just as much as our own. History offers glimmers of hope. The international collaboration to deflect asteroids like NASA's DART mission, which successfully nudged a space rock off course, proves we can unite across borders when the threat is clear enough. Similarly, the treaties that limited atmospheric nuclear testing in the 1960s show humanity's capacity for collective foresight. But cosmic risks demand more: a sustained commitment to planetary defense, early warning systems for stellar explosions, and perhaps even interstellar redundancy through off-world colonies. The deeper question isn't whether we can achieve this, but whether we believe we should. Some argue survival at any cost is naive, that civilizations, like species, have natural lifespans. Others counter that intelligence carries a duty to endure, to safeguard the fragile light of awareness in a vast and indifferent cosmos. Between these views lies a truth worth clinging to. Our moment in the universe's story is fleeting but not insignificant. Every decision we make, from deflecting asteroids to curbing carbon emissions, echoes beyond Earth, shaping whether the cosmos remains silent or one day hums with the chorus of 1,000 civilizations. In the end, existential risk isn't just about avoiding catastrophe. It's about earning our place among the stars, proving we're not just accidents of chemistry, but beings capable of steering our fate. The universe has given us a choice: perish as a footnote or persist as its most astonishing chapter. The next move, quite literally, is ours. There's a moment burned into the memory of nearly every astronaut who's looked back at Earth from space, a visceral, almost spiritual awakening they struggle to put into words. It starts with the view, a delicate blue marble suspended in endless black, its atmosphere no thicker than the skin of an apple, continents and oceans swirling beneath swirling veils of clouds. No borders visible, no noise of humanity's divisions, just a single, breathtakingly fragile oasis of life. This is the overview effect, a term coined by space philosopher Frank White, but the experience itself transcends language. Apollo 14's Edgar Mitchell described it as a sudden understanding that the molecules of my body and the spacecraft were manufactured in some ancient generation of stars, while ISS astronaut Ron Garan likened it to seeing the world through a spacecraft window frame, but also through a frame of mind. What makes this shift so transformative isn't just the sight itself, it's the collision of scale and immediacy. From space, Earth isn't a map or a globe, it's alive. Astronauts report seeing hurricanes churn like living creatures, the Amazon's deforestation scars burning like fresh wounds, and the nighttime glow of cities pulsing like a collective heartbeat. The cognitive dissonance is staggering. The planet feels simultaneously immense and tiny, enduring and vulnerable. Canadian astronaut Chris Hadfield captured this duality after his first spacewalk, realizing that his entire life, every person he'd ever loved, every place he'd ever visited existed beneath his fingertips, yet occupied less physical space than the dust on his visor. Psychologists call this cognitive recalibration, a seismic rewiring of perspective where abstract ideas like global unity or environmental stewardship become visceral truths. The effect isn't just emotional, it's physiological. Brain scans of astronauts show heightened activity in regions linked to empathy and interconnectedness, as if the cosmic vantage point short-circuits the mental shortcuts we use to separate us from them. This might explain why so many who have experienced it return as activists like NASA Nicole Stott, who founded the Space for Art Foundation, or Sultan bin Salman Al Saud, the first Arab astronaut, who became a vocal advocate for cross-cultural climate collaboration. Yet the most radical implication of the overview effect isn't about space travel, it's about replicating that shift for those of us grounded on Earth. Philosophers like Peter Russell argue that modern crises, from climate collapse to geopolitical strife, stem from a failure of perception. We're stuck in a flat Earth mindset, unable to grasp the systemic whole. But tools like the blue marble photo, virtual reality simulations of orbital views, or even biosphere visualization projects are bridging the gap. When researchers showed subjects VR experiences mimicking the astronaut's perspective, they measured measurable increases in pro-environmental behavior, as if the simulated view had injected a microdose of cosmic awareness. The overview effect also whispers a tantalizing possibility that cosmic perspectives might be evolutionary stepping stones for consciousness itself. Indigenous cosmologies have long understood this. The Maori see Earth as Papatuanuku, a living ancestor. The Amazonian Shipibo perceive the planet as a fractal tapestry of interconnected energies. Modern astronauts, often steeped in Western reductionism, echo these ancient intuitions unprompted. Perhaps there's something primal about seeing the whole, a latent capacity awakened only when the illusion of separation shatters. Critics counter that the effect is a luxury of the privileged. After all, only 600 humans have ever left Earth's atmosphere, but the democratization of space with civilian missions and orbital livestreams is already diluting that barrier. When SpaceX's Inspiration 4 crew non-professional astronauts returned speaking of transcendent awe and a renewed drive to address global inequity, it suggested the effect isn't confined to elite test pilots. It's a human response to a fundamental truth we've always known but rarely felt, that every forest, city, and child exists together on a life raft adrift in the cosmic dark. The ultimate lesson might be this: the overview effect isn't about leaving Earth, it's about rediscovering it. In a universe of barren rocks and lethal radiation, our planet isn't just home. It's a masterpiece of improbability, a singular sanctuary where stardust learned to dream. And you don't need a rocket to see that. Sometimes all it takes is tilting your head back on a clear night, tracing the arc of a satellite with your finger, and remembering you're already riding the most extraordinary spaceship of all. Standing beneath a sky crammed with stars, it's impossible not to feel dwarfed, not just in size but in significance. This visceral reaction, this trembling mixture of wonder and insignificance, is what philosophers have called the sublime for centuries. Immanuel Kant described it as the mind's paradoxical response to something so vast it overwhelms our capacity to comprehend. Yet in that very overwhelm, we find a strange expansion of our own imagination. Modern psychologists echo this, tracing aw's fingerprints in our brains the way it quiets the default mode network, the mental chatter of ego, and opens floodgates of empathy and connection. Astronomy, more than any other science, serves this emotion to us on a cosmic platter. Every image from the Hubble Deep Field, every gravitational wave detection, is an invitation to stand at the edge of the incomprehensible and let it rearrange us. Take the pillars of creation, those towering columns of gas and dust where stars are born. Seen through a telescope, they're magnificent. Understood as structures light years tall, they become transcendent. The knowledge that we're staring at a nursery of suns hundreds of trillions of miles away does something curious. It collapses the distance between abstract science and raw emotion. Psychologists like Dasha Keltner at UC Berkeley have found that awe reliably dissolves the boundaries of the self, making people feel more interconnected with others and more attuned to something larger than their daily concerns. It's no accident that astronauts returning from space often describe a desperate urge to protect Earth's fragile biosphere, or that Carl Sagan's pale blue dot speech still haunts us decades later. Awe doesn't just make us feel small, it makes our smallness meaningful. This isn't just poetic musing, it's neurobiology. When fMRI machines track brains immersed in awe, whether from standing in a cathedral, hiking a mountain, or watching a simulation of the Big Bang, they show decreased activity in regions linked to self-focus and increased activity in areas tied to collective identity. Ancient rituals harnessed this deliberately: star alignments in megalithic temples, solstice ceremonies, even the vaulted ceilings of Gothic cathedrals designed to mimic the heavens. Today, we've swapped stone circles for planetariums, but the effect is the same. Awe is the universe's oldest spiritual technology, and astronomy its most refined delivery system. Yet there's a tension here. The same cosmos that inspires awe also reveals our profound fragility. A single gamma-ray burst, a wandering black hole, or the slow death of our sun could erase everything we've ever built or loved. This duality, the sublime's simultaneous uplift and terror, is precisely what makes it so potent. Philosopher Edmund Burke argued that the sublime's power comes from this dance between attraction and fear, like standing at the edge of a cliff, pulse racing but unable to look away. Modern cosmology hands us cliff edges by the dozen: the event horizon of a black hole, the heat death of the universe, the sheer statistical unlikelihood that we exist at all. The gift of cosmic awe isn't answers, it's better questions. When we confront the universe's scale, we're forced to reevaluate what matters. Petty grudges, tribal divisions, even personal ambitions can seem absurd against the backdrop of 100 billion galaxies. But rather than nihilism, this perspective often births a quiet urgency. If our time is fleeting and our corner of space tiny, then every act of creation, connection, or curiosity becomes a rebellion against indifference. Astronomer Maria Mitchell put it perfectly in 1847 after calculating the orbit of a new comet. The universe is not just stranger than we imagine, it's stranger than we can imagine. And that strangeness isn't a wall, it's a door. Perhaps that's the sublime's final lesson. The cosmos doesn't diminish us by its enormity, it liberates us. In the face of such grandeur, we're free to shed the weight of self-importance and embrace something far richer: the chance to be momentary witnesses to a story older than starlight, and maybe, just maybe, to leave our own faint brushstrokes on its canvas. Galileo's famous declaration that mathematics is the language in which the universe is written wasn't just poetic flair. It was a radical claim that numbers and equations aren't merely tools we've crafted to describe reality, but the very fabric of reality itself. Centuries later, this idea still divides thinkers into two camps. On one side, the Platonists argue that mathematical truths like the elegance of pi or the symmetry of prime numbers exist independently, waiting to be discovered in some abstract realm beyond space and time. To them, the fact that a butterfly's wings echo the Fibonacci sequence or that galaxies spiral in logarithmic curves isn't coincidence. It's evidence of a hidden mathematical blueprint underpinning all existence. Yet skeptics fire back. If math is so fundamental, why does it sometimes feel like a game with arbitrary rules? Nominalists like philosopher Hartree Field insist mathematics is a human invention, a sophisticated mental scaffold we've built to make sense of patterns, nothing more. They point to the way mathematical concepts evolve over time, from Newton's calculus to quantum field theory, as proof that it's a language we're constantly refining, not an eternal truth we're uncovering. In this view, the universe doesn't care about equations. We impose them because they're useful. The debate isn't just academic, it shapes how we approach cosmic mysteries. If math is invented, then the quest for a theory of everything might be chasing a mirage, an ever-receding horizon of human-made models. But if it's discovered, then every breakthrough, from Einstein's relativity to the Standard Model, brings us closer to decoding reality's deepest secrets. Consider the uncanny effectiveness of math in physics. When physicist Paul Dirac scribbled equations for electron behavior in the 1920s, his solutions implied the existence of antimatter, a concept then unknown. Years later, positrons were found exactly as predicted. Similarly, mathematician Emmy Noether's theorem linked symmetry to conservation laws, revealing why energy can neither be created nor destroyed. These aren't just lucky guesses, they're moments where abstract math seems to tap into cosmic truths before experiments catch up. Even more striking is the Mandelbrot set, a fractal so complex it's been called the thumbprint of God, generated from a simple equation yet containing infinite, self-repeating patterns found in coastlines, clouds, and even stock markets. But counterexamples abound. Take the history of geometry. Euclid's parallel postulate was once considered an immutable law until mathematicians like Riemann and Lobachevsky dreamed up curved spaces where it didn't apply concepts Einstein later wielded to describe gravity. If math were purely discovered, how could its rules bend? Then there's the unsettling fact that some branches, like string theory's 10 or 11 dimensions, remain stubbornly untestable, drifting into the realm of mathematical elegance untethered from observable reality. Perhaps the truth lies somewhere in between. Cognitive scientist Rafael Núñez suggests math is a blend of invention and discovery, a biocultural phenomenon shaped by both the hardwiring of our brains and the universe's structure. After all, our neural circuits evolved to recognize patterns in nature, so it's no surprise our math reflects those patterns. Even the concept of numbers might owe as much to the human mind as to cosmic law. Some Amazonian tribes, like the Paraha, have no words for precise quantities yet navigate their environment flawlessly. The stakes couldn't be higher. If Platonists are right, then the universe is profoundly intelligible, its laws written in a code we're slowly deciphering, a code that might even hint at a deeper order or designer. If nominalists prevail, then reality is messier, and math is merely our most brilliant flashlight in the dark. Either way, every time a physicist scribbles an equation or a child solves for X, they're participating in an ancient, awe-inspiring dialogue. Are we uncovering the universe's native tongue, or are we forever translating its whispers into a language of our own making? The answer might determine not just how we do science, but how we define truth itself. Science thrives on taking things apart, atoms into protons, protons into quarks, galaxies into stars. This reductionist approach has unlocked wonders, from the double helix of DNA to the equations predicting black holes. But here's the cosmic curveball. What if some mysteries refuse to be sliced into smaller pieces? Imagine trying to understand a symphony by analyzing individual notes. You'd miss the harmony that gives them meaning. That's the heart of the reductionism debate. Can the universe truly be understood by dissecting it, or are there phenomena that only reveal their secrets when viewed whole? Take something as simple as water. Study a single H2O molecule, and you'll learn about hydrogen bonds and oxygen's electronegativity. But you'd never predict how trillions of these molecules together create the roar of a waterfall, the serenity of a dewdrop, or the way ice crystals form fractal patterns. These are emergent properties, qualities that arise from complexity itself, impossible to deduce from individual parts alone. Now scale this up to the cosmos. The Milky Way isn't just a pile of stars. Its spiral arms, star-forming regions, and dark matter halo emerge from gravitational dances spanning billions of years. Reductionism might map every star's position, but it can't fully explain why the whole feels so breathtakingly alive. Nowhere is this tension more striking than with consciousness. Neuroscientists can map synapses and dopamine pathways, but no scan explains why the firing of neurons creates the taste of chocolate or the ache of nostalgia. Philosopher David Chalmers calls this the hard problem, the gap between objective brain mechanics and subjective experience. It's like knowing every circuit in a computer without grasping how it runs a video game. Some theorists, like Roger Penrose, argue consciousness might harness quantum processes defying classical reductionism. Others suggest it's an emergent phenomenon where complexity itself births awareness, just as temperature emerges from atomic motion even though no single molecule is hot. The unsettling implication: we might need new scientific paradigms to even frame the question properly. Even cosmology grapples with this divide. The Big Bang model brilliantly reduces the universe's history to equations, but it stumbles over questions like why the constants of nature are fine-tuned for life. String theory offers a reductionist dream, a single theory of everything unifying all forces, yet after decades it remains untested, its mathematical elegance possibly just a mirage. Meanwhile, holistic approaches like loop quantum gravity suggest spacetime itself might emerge from deeper, non-spatial building blocks, like a 3D hologram projected from a 2D surface. The takeaway: the universe might not play by reductionism's rulebook. History reveals the limits of breaking things down. Newton's clockwork universe seemed complete until quantum weirdness shattered it. Today's particle colliders probe ever smaller scales, but what if the answers lie not in the fragments, but in the connections between them? Think of an ant colony. No single ant holds the blueprint for the nest's architecture, yet together they build cathedrals of dirt. Similarly, life might not reside in DNA's nucleotides alone, but in the dynamic interplay of cells, ecosystems, and even planetary cycles. This isn't to discard reductionism. It's given us vaccines, silicon chips, and Mars rovers. But embracing holism could unlock new frontiers. Climate science, for instance, thrives on seeing Earth as a single system, where plankton blooms and melting permafrost are threads in the same tapestry. Similarly, solving quantum gravity might require seeing spacetime not as a collection of points, but as a network of relationships. The universe seems to whisper a dual truth: to comprehend the very small, we must also honor the very large. Like a cosmic version of the blind men and the elephant, perhaps reality demands multiple ways of seeing, not just microscopes and particle accelerators, but telescopes, neural networks, and even the introspective gaze of philosophy. After all, isn't the greatest mystery of all that we're here to ponder these questions at all? Eastern cosmologies whispered truths about the universe millennia before telescopes peered into the void. Hindu scriptures describe a cosmos that breathes, expanding and contracting in cycles lasting trillions of years, each day of Brahma mirroring our modern concept of the Big Bang and Big Crunch. The Rig Veda even poses a question that still haunts physicists. What was the seed, what was the root before heaven and earth existed? This isn't poetic coincidence, it's astonishing foresight. Ancient Vedic astronomers mapped multi-layered universes with uncanny precision, their descriptions of lokas worlds echoing today's multiverse theories, where infinite realities bubble into existence like foam on an endless ocean. Buddhist cosmology takes this further, envisioning reality as an infinite web where every jewel reflects all others, a metaphor that eerily parallels quantum entanglement. In the Avatamsaka Sutra, the universe is depicted as Indra's net, where each sparkling node connects to every other, instantaneously responding to changes across vast distances. Modern physics confirms this isn't just philosophy. When two entangled particles remain connected regardless of separation, defying classical notions of space and time, science catches up to what meditators intuited centuries ago. The Dalai Lama often remarks how Buddhist concepts of emptiness, the idea that objects have no intrinsic existence outside their relationships, resonate with quantum field theory's revelation that particles are mere excitations in an underlying void. Taoist sages approached cosmic mysteries through balance rather than equations. The yin-yang symbol, often dismissed as simplistic, encodes profound astrophysics. Its swirling halves embody the dynamic equilibrium between dark and light matter, creation and entropy, even matter and antimatter. Lao Tzu's Tao Te Ching describes the universe as a bellows, empty yet inexhaustible, mirroring modern vacuum energy, the mysterious force accelerating the expansion of space. When Taoist texts speak of wu-wei effortless action, they're describing the same cosmic dance physicists see in celestial mechanics. Planets orbiting without motors, galaxies spinning without push or pull. What makes these parallels so electrifying isn't just their accuracy, but their methodology. Eastern traditions didn't dissect nature with microscopes. They turned inward, using disciplined observation of consciousness itself as their laboratory. Tibetan monks mapping subtle energy channels, Nadi's anticipated neuroscience's discovery of the default mode network, while Ayurvedic texts described quantum-like vibrational states of matter long before string theory. This convergence suggests something radical, that direct experience and empirical experimentation might be two paths up the same mountain, yet the differences are as illuminating as the parallels. Where Western science seeks to control and quantify, Eastern cosmologies emphasize harmony and acceptance. The Buddhist concept of pratityasamutpada, dependent origination, teaches that nothing exists independently, a truth ecology confirms when tracing how plankton blooms affect cloud formation. But while science measures these connections, Eastern philosophy asks us to feel them, to recognize our own breath as part of the cosmic rhythm. This fusion of worldviews might hold the key to tomorrow's breakthroughs. As physicists struggle to reconcile quantum weirdness with cosmic scales, they're venturing into territory long charted by mystics. The quantum vacuum's zero-point energy echoes the Hindu Akasha, the fundamental space from which all form emerges. Multiverse theories resonate with the Jain cosmological model, where innumerable lokas coexist like sheets of paper stacked infinitely thin. Even dark energy's mysterious push finds precedent in the Taoist Kai, the invisible force animating all things. Perhaps the greatest lesson lies not in who was right, but in realizing how many ways there are to know. When a 13th century Zen master like Dogen writes, "Time is existence and existence is time," he's articulating what Einstein formalized centuries later, that space-time is a seamless fabric. These aren't separate truths, but facets of a reality too vast for any single perspective to capture. In bridging ancient insight and modern data, we don't just expand our understanding of the cosmos, we rediscover our place within it, not as passive observers, but as conscious participants in an unfolding story much older than stars. Long before telescopes etched their lenses against the night sky, the Kalahari's sand people traced the celestial paths of the Milky Way, not as distant balls of gas, but as embers from a great fire lit by their ancestors. To them, the cosmos wasn't a cold mechanical clockwork. It pulsed with stories where the stars whispered warnings of droughts and the Pleiades signaled the time for harvest. This is the essence of indigenous star knowledge, an unbroken thread weaving precise observation with the sacred, where every constellation holds not just coordinates but meaning. Consider the Inuit of the Arctic, who navigated featureless ice sheets by reading atmospheric halos around the moon, a technique modern science now recognizes as detecting ice crystals in the air. Their star maps didn't just chart positions, they encoded survival. The constellation Ogjuk, 3 bright stars in a row, wasn't merely Orion's belt, it was a celestial landmark guiding hunters home through blizzards. Meanwhile, Polynesian voyagers crossed thousands of miles of open ocean using star compasses, memorizing the rising and setting points of hundreds of stars while feeling the swell of waves beneath their hulls. Their knowledge wasn't written in equations but sung in chants, passed down through generations like a living GPS. What makes these traditions revolutionary isn't just their accuracy, but their philosophy. Western astronomy often divorces the observer from the observed, treating the cosmos as a puzzle to be solved. But for the Maori of New Zealand, the Milky Way Te Ikaroa is the canoe of the god Tamariti, its stars flung from his fishing net. This isn't myth obscuring science, it's science enriched by narrative where cosmic patterns become moral lessons. When Aboriginal Australians speak of the emu in the sky, a dark constellation formed by dust lanes in the Milky Way, they're not ignoring astrophysics, they're layering it with ecological wisdom, linking the emu's appearance to egg-laying seasons. The clash between these worldviews reveals a deeper tension. Modern cosmology measures redshift and cosmic microwave background, while the Lakota people see the birth of stars as the breath of Why, the universal life force. One approach seeks dominion over nature's laws, the other seeks kinship with nature's spirit, yet both arrive at profound truths. The Maya calculated Venus cycles to within seconds, not just for celestial mechanics, but to time sacred ceremonies aligning human rhythms with cosmic ones. Their Dresden Codex contains tables predicting eclipses centuries in advance, blending math with metaphysics in ways that still baffle historians. This wisdom holds urgent lessons today. As light pollution erases the stars for a third of humanity, Indigenous star knowledge warns of what's lost when we sever our bond with the night sky. The Tswana people of Botswana call the large Magellanic Cloud Kegodi, a cosmic hearth reminding them of communal fireside teachings. In an age of satellite megaconstellations and vanishing darkness, their perspective reframes the sky not as a resource to exploit, but as a legacy to protect. Astronomers at the Atacama Desert now consult with local Atacamino elders, learning how their ancestors used the stars to manage water in Earth's driest place. A dialogue where quantum physics meets aquifer stewardship. Perhaps the most radical gift of indigenous astronomy is its democratization of wonder. Where modern science often gates cosmic understanding behind degrees and jargon, the Cherokee see every child as a potential Adando, a star keeper. Their stories teach that the Milky Way was spun by a grandmother spider, placing the cosmos within reach of the youngest listener. This inclusivity mirrors a truth too often forgotten, that the night sky belongs not just to those with telescopes, but to anyone who dares to look up and imagine. The challenge isn't to romanticize these traditions, but to recognize their sophistication. When Navajo astronomers speak of Nilchi, the cosmic wind connecting all things, they anticipate what quantum physics calls entanglement, the invisible threads binding particles across light years. Indigenous star knowledge doesn't reject empiricism. It embeds it within a tapestry of relationship where knowing a star's name is just the beginning of the conversation. As we stand at the crossroads of climate crisis and space colonization, these ancient voices offer a compass we'd be wise to follow, one that points not just to the stars but to our place among them. UFOs, or as scientists now prefer to call them, unidentified aerial phenomena, hover at the edge of our scientific understanding like shadows just beyond a campfire's glow. These aren't the stuff of grainy YouTube videos alone. Even the Pentagon has declassified footage showing objects moving in ways that defy conventional aerodynamics, abrupt zigzags, hypersonic speeds without sonic booms, maneuvers that would tear human-made aircraft apart. The key word here is unidentified. It doesn't automatically mean alien, but it does mean inexplicable with current data, and that's where the real intrigue begins. Take the U.S. Navy's encounter with a Tic Tac object off the coast of San Diego in 2004. Fighter jets tracked a white, oblong craft with no visible wings or exhaust plumes, accelerating from a hover to Mach speeds in seconds, far beyond known propulsion technology. Radar operators, pilots, and infrared cameras all corroborated the sighting. Skeptics pointed to sensor glitches or atmospheric phenomena, yet none fully explained the event. Cases like this force an uncomfortable question. How does science investigate phenomena that resist classification without tipping into credulity or dismissal? The tension lies in methodology. Science thrives on reproducibility, controlled experiments, peer review, and falsifiable hypotheses. But UAPs are ephemeral by nature, appearing unpredictably and leaving no physical traces. Astronomer J. Allen Hynek, who began as a skeptic debunking UFO reports for the U.S. Air Force, later conceded that a small percentage of cases remained unexplainable even after rigorous analysis. His solution: apply the same rigor we use to study rare cosmic events like supernova. Collect data systematically, rule out prosaic explanations, and crucially, avoid conclusions before evidence warrants them. This balancing act isn't new. When 19th century astronomers spotted canals on Mars, some speculated about intelligent engineers until better telescopes revealed optical illusions. Similarly, pulsars discovered in 1967 were briefly dubbed LGM-1 little green men because their precise radio pulses seemed artificial. Both examples show how the line between curiosity and conjecture blurs when faced with the unfamiliar. The difference today is scale. Advanced sensors and AI analysis allow us to scrutinize UAPs with tools unimaginable to Hynek's era. Yet the cultural weight of UFOs complicates things. Pop culture has spent decades equating them with alien visitation, from Orson Welles' War of the Worlds broadcast to conspiracy lore around Area 51. This baggage makes sober discussion fraught. Researchers risk ridicule if they engage seriously, yet risk negligence if they ignore credible reports. The irony. Some of history's greatest discoveries began as heresies: continental drift, quantum entanglement, even the heliocentric solar system were once dismissed as absurd. Perhaps the most valuable lesson UAPs offer isn't about extraterrestrials, but epistemology, how we know what we know. They expose gaps in our understanding of atmospheric physics, human perception, and even the limits of sensor technology. When military pilots report objects submerged one moment and airborne the next, could they be glimpsing unknown plasma phenomena or propulsion breakthroughs? The scientific method's strength is its humility. It leaves room for mystery, allowing anomalies to guide us toward new questions rather than forcing premature answers. In the end, UAPs serve as a mirror. They reflect our hunger for cosmic companionship, our fear of technological inferiority, and most of all our awe at a universe still full of secrets. Whether these phenomena turn out to be exotic natural events, classified aircraft, or something truly unimagined, their greatest gift may be the reminder that wonder and skepticism aren't opposites but partners in the dance of discovery. After all, the universe owes us no promises, only puzzles, and it's in the grappling with those puzzles that science, at its best, truly soars. The International Space Station circles Earth every 90 minutes, a shining symbol of what humanity can achieve when we look beyond borders. Up there, in the airless black, American astronauts work side by side with Russian cosmonauts, Japanese engineers, and European scientists, a harmony rarely mirrored in the geopolitics below. This wasn't always the plan. During the Cold War, space was just another battlefield, with rival superpowers racing to plant flags on the moon. But somewhere along the way, something shifted. The 1975 Apollo-Soyuz mission, where U.S. and Soviet spacecraft docked in orbit, marked the first thaw, a handshake in zero gravity that proved cooperation wasn't just possible but transformative. This isn't just about shared laboratories and solar panels. The ISS demonstrates something deeper, that survival in the cosmos demands interdependence. When an oxygen generator fails or a meteoroid shield cracks, no one asks about the crew's nationality. They solve the problem together or perish together. Astronauts often describe this as the orbital perspective, a visceral understanding that Earth is a single, fragile lifeboat adrift in an infinite sea. Canadian astronaut Chris Hadfield put it best: "There's no time for pettiness when you're floating 250 miles above everything you've ever known." That realization, that we're all riding the same spinning rock through space, has a way of shrinking terrestrial squabbles to insignificance. Could this perspective scale beyond the handful of souls who have experienced it firsthand? History offers glimmers of hope. During the 1968 Apollo 8 mission, when astronauts broadcast the first image of Earth rising above the lunar horizon, the iconic Earthrise, it ignited a global awakening. That single photograph, showing our planet as a lonely blue marble wrapped in fragile atmosphere, became a rallying cry for environmental movements and disarmament treaties. Even warring nations paused to marvel. Egyptian journalist Mohammed Hassanein Haikal wrote at the time that the image cracked the shell of our imagined differences, proving that national borders are human inventions invisible from space. Yet the leap from inspiration to systemic change remains vast. While space agencies collaborate peacefully, terrestrial conflicts over resources, ideology, and power rage on. Some argue this disconnect reveals a painful truth: that cosmic unity is a privilege of the few, accessible only to those wealthy or technologically advanced enough to reach orbit. Political scientist Daniel Dewdney cautions against space escapism, the naive hope that stargazing alone can solve entrenched conflicts. After all, medieval astronomers mapped the heavens while crusaders slaughtered each other below, proving celestial awareness and earthly violence can coexist. But perhaps the solution isn't all or nothing. Consider the overview effect, the profound shift reported by astronauts who see Earth from space as a social technology we can cultivate even groundside. Initiatives like the Overview Institute use virtual reality to simulate the astronaut's vantage point, with studies showing participants experience increased environmental concern and global empathy. Even simpler tools like the daily images from the ISS shared across social media serve as constant reminders of our shared home. When Ukrainian and Russian scientists continued collaborating on space telescopes even as their nations clashed, they proved that some bonds transcend politics. The real test may come as we venture farther. Artemis missions to the Moon and planned Mars settlements will require unprecedented international cooperation, from shared life support systems to mutual rescue protocols. These projects could become incubators for new models of governance and perhaps even prototypes for a post-national future. Visionaries like Carl Sagan dreamed of a day when space exploration would force humanity to mature, much as sailing ships once connected disparate cultures. The Voyager Golden Record, carrying greetings in 55 languages and sounds from across Earth, embodies this ideal, a message not from any one nation but from the planet as a whole. Skeptics will say this is utopian, but look at how satellite technology has already united us. GPS guiding ships from every nation, weather satellites warning of typhoons regardless of borders, the internet stitching together a global conversation. These weren't acts of charity, but of enlightened self-interest, proof that cooperation in space pays dividends on Earth. The challenge now is to extend that logic beyond infrastructure into identity. When a child in Nairobi and a grandmother in Oslo can both point to the Perseverance rover on Mars and say, "That's ours," we'll know the cosmic perspective has truly taken root. The stars won't wait for us to solve our petty conflicts, but every time an astronaut floats to an ISS window and sees Earth without divisions, just continents, clouds, and endless ocean, they glimpse the simplest and hardest truth of all: we're in this together, whether we act like it or not. The universe doesn't care about our rivalries. It only offers a choice: grow up or fade into the cosmic dark. The James Webb Space Telescope has already shown us galaxies sparkling at the edge of time, their light stretched into infrared whispers from the universe's infancy. But this is just the overture. With next-generation observatories like the European Extremely Large Telescope and the Square Kilometre Array coming online, we're not just extending our vision, we're rewriting the cosmic playbook. Imagine mapping the atmospheres of exoplanets light years away for signs of oxygen, methane, or even industrial pollutants, or detecting gravitational waves from colliding supermassive black holes, disturbances so vast they ripple spacetime itself like a pond struck by a mountain. Each new instrument is a key turning in the lock of reality, revealing chambers of existence we didn't know existed. Artificial intelligence is accelerating this revolution at light speed. Machine learning algorithms now sift through petabytes of telescope data, spotting anomalies human eyes would miss, like the mysterious, fast radio bursts that may be cosmic lighthouses from distant civilizations. AI doesn't just process information, it dreams in possibilities. At SETI, neural networks analyze radio signals for non-random patterns, while at CERN, they help simulate quantum foam fluctuations that might hint at extra dimensions. The irony is delicious. We're creating silicon minds to help our carbon-based ones grasp truths that may shatter our current physics. Yet the greatest discoveries often come from unexpected corners. Consider dark matter, invisible, intangible, yet comprising 85% of the universe's mass. Future detectors buried in abandoned gold mines or floating in space might finally catch these ghostly particles or prove they don't exist at all, forcing us to reinvent gravity itself. Or ponder the holographic principle, the radical idea that our three-dimensional universe is a projection from a two-dimensional boundary, like a cosmic Instagram filter. If proven, it would mean every star, every planet, even your morning coffee, is fundamentally an illusion, information painted on the surface of something far stranger. The search for extraterrestrial intelligence stands at a similar precipice. After decades of silence, initiatives like Breakthrough Listen are scanning millions of stars with unprecedented precision. But the real game changer might be technosignatures, evidence of alien engineering, like Dyson spheres harvesting star power or atmospheric chemicals betraying industrial activity. Some astronomers speculate that advanced civilizations could manipulate pulsars into galactic Morse code, or leave monoliths on lifeless worlds as cosmic "we were here" markers. The moment we confirm we're not alone wouldn't just answer a question, it would detonate our anthropocentrism like a supernova. Philosophically, this relentless probing raises profound questions about the nature of knowledge itself. Every time we've assumed we're at the pinnacle of understanding, from Ptolemy's geocentric universe to Newton's absolute time, the cosmos has laughed and shown us otherwise. The next paradigm shift might reveal that dark energy is the shadow of parallel universes brushing against ours, or that quantum entanglement proves consciousness is woven into spacetime. Perhaps the ultimate discovery will be that the universe isn't just stranger than we imagine, but stranger than we can imagine, a fractal labyrinth where each answer spawns 10 new mysteries. Yet for all our tools and theories, the most vital instrument remains human curiosity. It's the spark that led a young Einstein to wonder what it would be like to ride a light beam, and that drives today's researchers to spend nights debugging algorithms that might glimpse the birth of time. This blend of awe and tenacity, what Carl Sagan called the balance between skepticism and wonder, is our true spaceship. Whether decoding the quantum gravity or decoding an alien message, we're not just observers of the cosmos. We're its way of interrogating itself, one hypothesis at a time. The universe may not owe us answers, but it can't stop us from asking better questions. And that, perhaps, is the most human thing of all. From the moment our ancestors first traced constellations in the flickering campfire light, to the era of quantum telescopes peering back to the dawn of time, humanity's dance with the cosmos has always been as much about inner discovery as outer exploration. Those ancient star maps etched onto cave walls and clay tablets weren't just practical tools, they were the first philosophical treatises, wrestling with questions of origins, purpose, and our fragile place in the void. Fast forward to today, where astrophysicists grapple with equally profound mysteries wrapped in mathematical elegance. The event horizon's paradox, the quantum vacuum's hum, the eerie fine-tuning of universal constants. What's astonishing isn't how far we've come, but how consistently the stars have mirrored our deepest existential quandaries across millennia. Consider the parallel journeys of two seekers, a Babylonian priest tracking Venus's cycles to discern divine will, and a modern cosmologist measuring dark energies pushed to test multiverse theories. Both are fundamentally asking the same question: what forces shape reality, just through different lenses. The priest saw gods moving celestial bodies as signs. The scientist sees equations unfolding across space-time. Yet both share that electric moment of revelation when patterns click into place, bridging the known and the unknown. This is the secret alchemy of astronomy and philosophy. They transform cold data into meaning, whether through myth or mathematics. The stories we tell about the cosmos inevitably reflect our own evolving consciousness. When Ptolemy placed Earth at the universe's center, it wasn't just bad science, it was a metaphor for human exceptionalism. When Copernicus dethroned us, he didn't just rearrange planets, he triggered an existential crisis that still echoes in every SETI scan for alien intelligence. Even now, as we simulate black hole mergers in supercomputers or debate the simulation hypothesis, we're not just solving puzzles, we're refining what it means to be a thinking speck in an indifferent universe. The equations may describe quarks and quasars, but their implications ripple through every aspect of human life, from ethics to art. There's a poetic symmetry to how cosmic inquiries loop back to humble wonder. A child asking why the sky is dark at night, Olber's paradox, leads us to the expanding universe's finite age. A philosopher's thought experiment about brains in vats morphs into serious debates about holographic universes. Even the search for extraterrestrial life circles back to our own identity. Would finding microbial Martians make us feel less alone, or more acutely aware of the chasm between mere existence and conscious understanding? The universe refuses to be compartmentalized. It spills from telescopes into poetry, from particle colliders into meditation cushions. So tonight, when you step outside and look up, try this. Hold two thoughts simultaneously. First, that you're standing on a rocky sphere hurtling through space at 67,000 miles per hour, itself one of billions in a galaxy among trillions. Second, that your very act of observation, your curiosity, your awe is the universe's way of comprehending itself. That tension between scale and significance isn't a contradiction, it's the heartbeat of cosmic inquiry. Whether you're deciphering relativity or simply marveling at Orion's belt, you're part of an unbroken lineage that stretches back to the first human who ever squinted at the Milky Way and felt the delicious vertigo of the infinite. The cosmos doesn't just surround us, it dwells within us, in the questions we dare to ask and the humility to admit how much remains unknown. So keep looking up, but also inward. After all, every great astronomical revolution began the same way, with someone refusing to accept that the mystery was beyond reach. What will your refusal uncover? The next chapter of this grand dialogue waits not just in distant nebulae, but in the quiet space between your next thought and the stars overhead. The conversation has been going for 100,000 years, and